Hey, John here. Now, we've already talked about what it means to open and read and write files with formatted text. Let's talk now about binary data. What does it mean if I want to write the value of a structure of data in just raw binary, just write that out into the file? Well, we have ways to do that as well. So let's see what we've got going on here. I created a struct. It's got some what we call pod in here, plain old data, integers, characters, floats, doubles, things like that. And we create an fstream object. We open it up. Notice this time we say binary. On some operating systems, they like to screw up all your data in your file and help you if you're writing text into it. And because of that, we need to differentiate, like I said, in some cases, between binary files and non-binary files. On Unix systems, I'm not aware of anything that's different whatsoever between non-binary and binary. In Unix, one of the fundamental philosophies is that everything shall be the same. All files are simply files. Other operating systems that had a different origin tried to help the user by confusing them, which seems to be a common theme in a lot of modern languages. My point is, therefore, we have to specify that our intent is to read and write binary data and not to ask the operating system to mess with us and assume that we know what we're doing. That may be a mistake in itself, but that's a different, whole different conversation. Anyway, moving on. We're going to use binary data, so we tell it we're going to use binary data, just in case it's necessary. I'm going to create an instance of our data struct. We're going to fill in its values. I choose to fill in values by specifying them in hex. I've talked about this before. It'll make it much easier for us to see what the heck we're looking at when we're looking at hexadecimal dumps, like hex dump minus big C, on this file that we're going to create to see what went into it and where, okay? So put stuff in that you can easily recognize. What do we got going on here? There's 3 integers with these values. I'm going to use string copy to put this C string into this character array of 12 bytes. Notice there's exactly 11 items here. Don't forget about the trailing null. String copy writes all these characters plus the trailing null into the target address over here on the left. I'm then going to come down here and I'm going to execute write. Okay, so instead of this insertion and extraction operators and all that rigmarole and formatting and all the helpfulness that you get when you're doing text, which is great by the way, but in this case it would only get in our way, we're going to just say write this raw naked data structure in the form that it is while it's sitting in memory over here, or specifically right here in this local variable in main, by giving the address of that structure, that object. And then we're going to tell it, here's how many bytes to write into the file. It makes sense to just put the size of D. I want to put an instance of D. I want to write all the data in that structure into this file. How many bytes? Well, it's whatever the size of D is. It turns out to be 12 plus 4 plus 4 plus 4 in this particular operating system, because each of these integers are 4 bytes long. Okay? What's up with this piece of junk? Okay, well, this is very annoying in my opinion. I think what we're looking at here is the fact that C++, and in particular the write call for the output file stream, may have been invented and shared publicly as a library before void was invented and added to the C and C++ languages. I suspect that is the case. And the reason I suspect that is the case, because how often in the universe would you ever need to write raw naked binary data that is a character pointer? If you look at this formal spec for the write method of the output file stream, this first argument is a constant character pointer. The second one is a size t. All right? By making this a character pointer, the compiler will warn and or generate an error if you don't give it the address of a character in this argument here. My point is, you never use this, practically never to use this to write out just character arrays, okay? You'd use the insertion operator, probably, if you wanted to do that. So what we need to do is we have to use what's called a reinterpret cast. If you just put a static cast in here, it won't work. A reinterpret cast says to the compiler, just interpret this as if I were giving you a character pointer rather than the kind of pointer that I did give you. Okay. Now you could just as easily just smack it in the head and use a C-style cast like this and put oops, I'm on the wrong line, and do something along the lines of this. Quite often I'm personally very lazy and I'll do this. That's considered, arcane by today's standards, okay? But I'm over the age of 30, so everything I do is arcane, I guess, okay? Anyway, point is, this is the correct way to do this. Reinterpret what I've given you as if I gave you one of these things, because otherwise the compiler will gripe. In fact, let's go ahead and show you the error so you recognize it when you see it in the future. Come on, I can't even create an error when I want to. Come on. How often is that really a problem, right? Oh, I really want to have a problem. So this is what you get. It says, I don't know how to make a data star out of a char star. All right. That is the error that you will get, and you can solve it in this particular case by saying, look, I know you want a character star, but I'm going to give you a data star because I know what I'm doing, okay? I want you to write the contents of memory starting at this address, and I want you to write this many bytes. So that's what this means when we have a reinterpret cast on there, all right? Okay, let's run this. Oh, let's finish looking at what we're doing, okay? All right, so we're going to write that out. Then what am I going to do? I'm going to update. I'm going to put some new values in there, replace the contents of the structure, and I'm going to just write out a second time, then I'm going to close it, okay? We just compiled it. Oops, let's run it. Okay, it didn't do anything. Why? Because it didn't print anything or didn't read anything from the keyboard or anything. Now we see this data bin file sitting here. If we cat this out, God knows what it'll say. It's a binary file. We got some junk in there. That's nice. It's coincidental because the data that I wrote in there, like 30, 30, 30, 30, in hex is the number 0, all right? You can see the string ABCDFJ, and you can see this hello in there. And, there's no carriage return at the end of the file, so the prompt is over here. This is the kind of thing you'd see with a binary file. Sometimes you see little smiley faces and graphic junk, and the terminal could go nuts. In this particular case, it's relatively benign because I didn't do that much crazy stuff when I filled up that file with data. But nonetheless, you can't really look at it because it's binary by definition. So what did I write in there? Remember the 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, 2, 3, 3, 3, 3, 3, and then there's the A, B, C, D, E, F, G, H, I, J, K. 6B here is this K. All right. And this 0, 0 right there is the null terminator that string copy put into the 12-character buffer at the end of that structure. So if you look at the structure kind of in your head, you got a 4-byte integer, 4-byte integer, 4-byte integer, 12 bytes, which is 4 times 3, right? That's 4 times 2, 4 times 3. It should end exactly right there. And then we reset all the values in the structure, and we write it out again. And there's a little hello. When we wrote the hello in there this time, by the way. So here's the 30, 30, 30, 30, H-E-L-L-O, 21, and it's an exclamation point. And the null character right there is the character that got put in there by string copy. And by definition, string copy does not write anything else beyond what you told it to. And because this HIJK and this null was in the buffer before, it doesn't upset that. So when I write this whole thing out there, where did this come from? It came from my program. That's what it was supposed to write, okay? That's another great trick question for quizzes and tests and things like that. If you do this, what are you going to get? Well, you have to look at what happened before, right? Because this string copy right here writes HELLO bang and a null on top of this, which is there before, and this residual stuff is still there, okay? So this is how done, right? Brain dead simple. You just write what you want in there. The only thing interesting right here that you're learning right now, I guess, is that we can put it in a binary mode so that some operating systems that have to be told to be quiet and stand down do so when we're writing binary data. And we use write instead of the insertion operator, okay? And when you're writing, because the way it's defined, as I explained, we have to give it a char star or a const char star and rather than any other kind of pointer in here. So you can just say, look, just reinterpret it so that it is as I want, not as what you want it to be, okay? All right, so now let's look at this program, right? We wrote data into a file, and we can read data back out. Now we have an IF stream, okay? I'm going to call that IS. I'm going to open it up, okay? Again, I'm going to put it in binary mode. Don't help me. I know what I'm doing. I've got my exact same structure I did before. You can see that right up here. And again, games with the reinterpret cast. And we say, look, I want to read this time. I want you to read in and put in this pointer address. I want you to overwrite the contents of this structure for this many bytes. I want you to read that out of the file. Just stick it here, please. Thank you very much. Okay. Then I'm going to print out the fields. I'm going to read it again. I know there's 2 in there because I wrote the program myself and I put 2 in there. If you wanted to, you can. We could play. I tell you what. I'll do this in a loop in a minute, so we don't lose track of what's going on in this example here. So I'm going to read one of them. I'm going to just print it out. I'm going to print these integer values and this out as a C string. We already talked about all this stuff. The only thing new in here is this word right here, okay, and the fact that we're using an input file stream instead of an output file stream. The only thing that changed in here, okay? So let's go ahead and compile it up. Run this thing, and if I type correctly, we'll see some stuff. All right, here's these values. Why do they look like garbage? Well, they look like garbage because I printed those in decimal. Remember, I wrote them in hex. Now, you can get these things back out in hex form if you want. What is it? Standard hex. Let's go ahead and just print these out in hex. Certainly don't want to print the strings down here in hex. That would not make any sense at all. Oops. And now it makes a little more sense. If I told it to print it out in hex, 1s, 2s, 3s, 10s, 20s, 30s, and you see these strings. Now, the interesting thing about the hello, remember, a C string, it prints all the characters until it reaches the null. Now, you and I know that the H, I, J, and K are actually still sitting in that file, right? What do we want? That's that binary file. What was it called? Data.bin. Yeah, good name for it. Right? This H, I, J, K, and the null don't get printed out because the definition of what it means to print a string out, okay? Now, the neat thing, if you get into computer security and all that other fun stuff, if this was a database and you were updating a record in there, okay, and you wrote over, you know, an existing one, and you'd see this residual stuff over here, that can be a security problem. That does give you a clue of what was there before somebody wrote hello in there. If you're ever writing a short string on top of a long one, you might have a problem with security, okay? What if that was a part of a password or something? I mean, that's a bad idea, right? So here's what you really should do. I did this on purpose to show you that. You can use this to communicate with other people. This is sometimes called a subliminal channel. If you use stir-n copy, we talked about this before. This will always say, look, copy exactly the number of bytes I told you and no more from this string, okay, into this destination. So what size should I put in here? You might think, oh, I'm going to hard code it to 12, but that's a bad idea. You want to use this. If you're going to do this, you say size of the thing you're copying into, right? And I'll do that down here. The first one's not really a problem in this specific program because we copy exactly the right amount anyway, and I did that on purpose, okay? This second one, however, we're copying less than we want because it would be nice to just pad this out and erase what was there before. I want to completely erase the whole thing would be a nice thing to do when we're doing this and we're writing it out the first time. So let's go ahead and compile that one again. And I don't know what the heck is wrong here. Too many arguments. Oh, I forgot to put the N in there. And the second one, I guess. Okay. Oops. Hard to code while talking. All right. Remember what this thing does, right? It opens for binary. And it will truncate and replace what's in the file if it's already there, right? Because that's what happens if I open for data bin binary and I didn't give you any other way to prevent that from happening. I talked about that at great length at the end of the file I/O with formatted text video before this one. All right. So therefore, clear this mess out of here. Capital C would be nice. And we look at it now, and we will see the prior data has all been blanked out. It's all been nulled out, okay? This is a better way to update an existing file, or even in your running program. This is not really limited to just files, you know. If you're sending this data over TCP sockets or anything else between objects in your own program, and you don't, you know, pad out the remaining space in here, you're giving pointers to subroutines, functions, and libraries that have things in those buffers that may not, that might be that it shouldn't be that way, right? So, you know, you got to be careful when you're managing all your own buffers meticulously, like I'm doing this right here. If you're going to do everything on your own, you need to make sure that you're thinking about what happens, you know, outside the box, so to speak. And make sure that you're not sending junk data where you don't want it to go, because somebody might take advantage of that in some way. And to show you that it still all works fine is we'll run it again. And of course, this doesn't look any different at all, because again, the hello ends when you reach that null. The hello, the printing, the consumer prog 2 doesn't really look over here. Okay. My point is, but it could. So, you know, you should be thorough when you write your code. Now, all right, so I said, let's put a loop in here. Okay, let's copy this over so I don't break this file. You never know, I might need it for a demo some other day. Copy it over to prog 3, edit prog 3. And, you know, everybody knows you shouldn't really just be hard coding stuff. How does this work in a loop? Well, this read call, like everything else, returns a status. And if the thing succeeds, we can continue in our loop. Otherwise, we can fall out the bottom, close it, and go home. All right, so let's go ahead and update our makefile. And we can see it goes around and around and around in the loop for as many times, oops, as that read succeeds. All right. Okay. Again, do this until we enter into a failed state, which is I can't read anymore in this particular case. If you want to put, you know, the EOF jazz in here, then what you're going to have to do is you're going to have to write input. You're going to have to put a priming read. I see a lot of students not doing this when they put this in here and they type like this. And this is a failure on multiple fronts anyway, because if the read fails for some reason other than the end of file, then this may never go into an end of file status, and this could spin uncontrollably. I went on at this at great length when I said, you know, let's figure out how to read from standard CIN. All CIN is an IF stream anyway. So everything we've been talking about here is this exact same situation with reading from CIN and writing to Cout. Okay, so this should also work fine. If you screw up and you forget to do your priming read, which is incredibly common, then you get garbage data followed by good data. If you put the read up on the top of your loop, which is the double damage here, oh no, I need to do this because it has to read it before I print it out. Then you don't find out you've hit end of file until it's too late. In this particular case, you'll see the last item being processed twice, or you could end up with garbage in your program depending on how sloppy you are when you wrote this code. All right. So if you want to do this, you have to do it right, and you end up with all this extra junk in your code, which is why I never do it at all. And you just do it like this and put it all together nice and clean and like that. Less code means less problems. Okay, write less code, then you document less code, then you have to understand less code, which means if you have one error per line of code, you've just made 2 less errors when you're debugging your code. All right, so everything else we talked about file I/O in the prior video applies here. You can seek around and read and write these things anywhere you want. We don't need to reproduce all that here. That's all there really is to doing binary I/O. There's just no pre-made formatting routines that you can take advantage of. You have to use read and write and handle them yourself. Well, thanks for watching. See you next time.